So in this question, we have a graph generated from the scores table, and each node corresponds to a student, and the node is labeled by the sequence number of that particular student. So there is an edge between two nodes in the graph if the difference in the physics marks of the corresponding students is at most 5, and we need to complete the pseudocode. So let's see what's happening. We have the variable marks here, that is storing the return value of this particular procedure, read physics marks. And in read physics marks, you are initializing an empty dictionary. Then you are going through each row in the table, and the keys are nothing but the sequence numbers of the students. And for each student key, we are assigning the physics mark of that student as value, and we are returning the dictionary marks. So marks now holds the physics marks of all students in the class, keys being the sequence number and values being the corresponding physics marks of that particular student. So what is this line doing? So keys of marks will return the list of sequence numbers, or the list of keys in marks. That's nothing but the list of sequence numbers. Length of that will return the number of elements in that list. So in this case, n is nothing but the total number of rows in the table, right? Now this is what we have to fill, and let's directly go and see what the solution is. So in the first line, we create the matrix. A is now a matrix. We'll have a lot of, everything will be 0 to begin with. It will be an n by n square matrix with zeros everywhere, right? So we go through each I in the keys of marks, and within that we have another for each, which goes through each j in keys of marks, right? We have a nested iteration because we need to compare pairs of students. So given I comma j, what we need is to find the difference, that is nothing but this absolute value here, and there is an edge between I and j if and only if this condition is satisfied, right? So whenever this condition is satisfied, we have aij equal to 1, right? We set aij equal to 1, so there is an edge between I and j. Now how did this morph into this? How did this morph into this? Right, so when the absolute value is less than or equal to 5, then the entry inside will lie between -5 and 5, right? Both endpoints included, it's a less than or equal to, right? So that is all we have. So the other options are wrong because here there is only a less than, whereas we need at most 5, so that is why this option is wrong. This option is wrong because we are not creating the matrix at all, so that is why this option is wrong. Here we are creating the matrix, fine, but so marks of I minus marks of j should be between -5 and 5, whereas here it's between 0 and 5. So that ends the solution to this question. So in this question, we have a table of student scores. The first column gives us the serial number, and the corresponding cell in the score column gives us the score of that particular student. So for example, here this student with serial number 0 has scored 50, and the student with serial number n minus 1 has scored 89, right? So there is another information that is important which is given to us. So the actual scores in the table might be different. This has been given only for illustrative purposes, so we have to refer only to the table's header to answer all the questions. The information in this table is stored in a dictionary S. The serial numbers are the keys, and the corresponding scores will be the values, right? And we now generate a graph using this table. So how do we do that? Or given a pair of students I comma j, there is an edge from I to j if and only if i's score is strictly greater than that of j, right? So this is important to note. This is a directed graph, that is the edges have direction, and there is an edge from I to j, starting from I and ending at j, if and only if the score of I is strictly greater than that of j. Okay, so now we have a matrix A corresponding to this graph. Let's see how this pseudocode works here. So to begin with, we have n equal to length of keys of S. What does this mean? Keys of S is nothing but the list of keys in the dictionary S, and the length of that particular list is giving us the total number of elements in the list keys of S. So what does this mean? This is nothing but the total number of students in the table, right? So that is what n is storing here. And now we create a matrix of size n cross n. So initially all entries in the matrix A will be 0. Okay, now we iterate through each row R in A, and for each R we go through each column C in A, and if the score of student R is greater than the score of student C, then we add an edge from R to C. That's important. R to C. Therefore, A of RC we set it equal to 1. Now, what does this mean? There is an edge from R to C, right? So, the rth row cth column, or the cell which is in the rth row and the cth column, that is set to 1. Okay, row R column C, that particular cell is set to 1. So the first question that we have based on the pseudocode is this: a row R of the matrix has 3 entries that are 1, rest being 0. Okay, so what does this mean? Let's say that there are these 3 students in row R, right? So exactly 3 of them are 1, right, in that particular row. So let those columns be J1, J2 and J3. What does it mean that these cells are 1? A of rj1, A of rj2 and A of rj3, all 3 will have the value 1. Okay, so what does this mean in the graph? In the graph, it means that there is an edge from R to J1, there is an edge from R to J2, and there is an edge from R to J3, right? So we must be able to go back and forth between the graph and the matrix representation of the graph, right? So what does it mean to have an edge from R to J1? It means that R has scored more marks than J1. Putting it the other way, J1 has scored less than R. J2 also has scored less than R. J3 also has scored less than R. So we can see that there are 3 students who have scored less than R. But how do we know that there are exactly 3 students? This is because if there were to be one more student, say J4, who had scored less than R, then A of R J4 would also have been 1, right? That would have made 4 ones in the row R, which is not the case, right? So there are exactly 3 ones in row R, which means there are exactly 3 outgoing edges from R, which means there are exactly 3 students who have scored less than R. That's the correct answer. Moving on. So if R and C are 2 students with unequal scores, then what can we say? Right? So since R and C have unequal scores, we have one of these 2 possibilities. Either student R has scored more than student C. In this case, there is an edge from R to C, or A of RC equal to 1. And naturally, A of CR is equal to 0. The other possibility is student C could have scored more than student R. In this case, there is an edge from C to R, so A of CR is equal to 1 and A of RC consequently becomes 0. Right? We are asked if there is at least one row that has only zeros in it or ones in it, and there is also another option which corresponds to the columns. Do we have at least one column that has only zeros in it or ones in it? Right? So to answer this question, let's look at a student P who has scored the minimum marks in the class. And let's analyze the row for this particular student. Right? So the row P of this matrix will have only zeros in it. That is the claim that we are making. Why is this the case? So if student P has scored the minimum marks in the class, then the student's score will be less than or equal to the score of every other student I in the class. Right? Or S of P, the score of P will be less than or equal to S of I for every value of I from 0 to n minus 1. This is what it means for student P to have scored the minimum marks in the class. This means that there can never be an edge from student P to any other student I. Right? There can never be an outgoing edge from P to any other student. Why is this the case? Remember that we have an edge from P to I only if the score of P is strictly greater than the score of I. Since the score of P is always less than or equal to the score of I, we do not have any edge from P to any other node I. Sorry, we do not have an edge from P to any other node I. So P has no outgoing edges, which means that A of Pi, right, will be equal to 0. What is A of Pi? It is the ith column in row P. It is the cell corresponding to the ith column in row P, right? So for all the cells in row P, you will have only 0. So there is a row which has only zeros in it, and this row corresponds to a student who has scored the minimum marks in the class. Likewise, let us consider student Q who has scored the maximum marks in the class, right? And let us analyze the column Q of the matrix. Now our claim is that column Q has only zeros in it. Now why is this claim true? Again, we use a similar argument. Since Q has scored the maximum marks in the class, the score of Q is going to be greater than or equal to the score of I, right? So S of Q is going to be greater than or equal to S of I because Q has scored the maximum marks. What does this mean? This means that you can never have an edge from any node I to Q. In other words, Q cannot have any incoming edges. Okay, so when can Q have an incoming edge? Only if there is a student I who has scored more marks than Q. Since Q has scored the maximum marks in the class, there can never be any student who has scored more marks than Q. Therefore, Q will not have any incoming edges. What this means is that A of IQ will be 0 for all I. A of I, remember that A of IQ is 1 only if there is an edge from I to Q. Since we can never have an edge from I to Q, A of IQ will be 0 for all I, right? And that ends the solution to this problem. Okay, so this is a continuation of the previous question. Okay, so we assume that the matrix A has already been computed and we are given some very cryptic pseudocode here. All right, so before we go ahead and see what is happening, let's first take an example. So consider this table here, right? So this table has the scores of 5 students. Okay, this is the graphical representation of the table, and this is the matrix representation of the graph that is shown here. Okay, so I have just used these two windows so that it becomes easy to see what's happening. All right, so let's focus on the scores here, and let's focus on the graph and the matrix here, right? So if you notice, student 0 has scored 70, 150, and so on. Student 4 has scored 80. So the student who has scored the minimum marks is 3 with 40, and the student with maximum marks is 4, 80. Okay, so how do we generate this graph from the table? Let's see how we are doing that. Let's take student 0, right? So there is an edge from 0 to some other student if the particular student 0 has scored more marks than the other student. Or rather, is there an edge from 0 to 1? Yes, right? Because 0 has scored more than 1, 70 greater than 50. So there is an edge from 0 to 1. As you can see, it's a directed edge from 0 to 1. So 0 has also scored more than 2. So there is an edge from 0 to 2. Likewise, 0 has scored more than 3. Therefore, there is an edge from 0 to 3 as well. Okay. So there are 3 outgoing edges as far as 0 is concerned. Now, we can see that there is only one incoming edge for 0, which means that there is exactly one student who has scored more than 0, and in this case it is student 4, right? So student 0 has one incoming edge, that is there is an edge from 4 to 0, right? It comes into 0, and 0 has 3 outgoing edges. That is, it goes out of 0, right, to 1, 2, and 3. All right. So let's now go to the matrix representation of this graph and see how it works, right? So there is 0, 0. There is no edge from 0 to 0, so that entry is going to be 0. There is an edge from 0 to 1, all right? So there is a 1 corresponding to that entry here. There is an edge from 0 to 2. Again, there is a 1 here in the matrix. And there is an edge from 0 to 3. There is another 1. Since there is no edge from 0 to 4, that entry is 0. Okay. So if you look at a row of a matrix corresponding to an element, say 0, that will give you an understanding of all the outgoing edges, right? By looking at the row of a matrix, you can get to know about all the outgoing edges of a particular node, right? So what we'll do now is, let us go from the matrix to the graph, right? We should also be able to do that. So for example, let's look at node 1, and if you look at the row corresponding to node 1, we must be able to tell how many outgoing edges it has and what are these outgoing edges. So it is clear that 1 has exactly this one outgoing edge, that is 1 has an outgoing edge to 3, 1 to 3. So our graph should be exactly that. So if you notice, there is exactly one outgoing edge from node 1 and it goes to 3. Okay, so what about the incoming edges? Now if you look at the column of a matrix, you will get to know all that you need to, you will get all the information that you need about the incoming edges at a given node. Let's again take the case of node 1. There are 3 non-zero entries. So there must be 3 incoming edges, right? And what are these? These are from 0 to 1, 2 to 1, and 4 to 1. Are we correct? Is there an edge from 0 to 1? Yes, there is. Is there an edge from 2 to 1? Yes, there is. Is there an edge from 4 to 1? Yes, there is. Right? So this way, we can keep moving back between the graphical or visual representation and the matrix representation. Right? So this is something that must become very comfortable to you, moving across these two representations. Okay, so now that we have this information with us, let's go back to the pseudocode. Okay, so in the pseudocode, let's see what's happening. We start with n being the length of keys of S. Again, this is nothing but the number of elements, a number of students or some in the class, or the number of rows in the table. Okay, so we start with the number of students or the number of nodes in the graph. K is initialized to 0 and sum score is nothing but the score of student 0. We have walk being set to true, it's a binary variable, and hops is initialized to 0. Okay, in the first iteration, the first step of the while loop, walk is true, so we are going to go in, and immediately after entering the loop, walk is set to false. Okay, so now we come to this for each. Let's see what's happening. We are going through each C in the columns of A. Okay, and if there is an edge from K to C, then we are going inside and doing something, right? So what is it that we are doing if there is an edge from K to C? We are updating K to C, that is K is equal to C, and then we are updating some score to be the score of student K, right? And we are updating walk to true, right? Incrementing hops, and then we are exiting the loop. So there are a lot of things going on here. Let's take this example that we have and see what's happening. So initially walk is true, so we enter. Remember that K is 0, so focus on the node 0 here. For each C in columns of A, so we are going to loop through 0 to 4. If A of KC is double equal to 1, right? KC now in this case is nothing but A of 0C, right? A of 0, 0. Since C equal to 0 will be the first in columns of A, we are asking if A of 0 0 is 1, it is not 1. So we go back, we take up the next element in columns of A, it is 1. So if A of 0 1 is 1, then we go inside the if block. In this case it is 1, so we enter the if block. Okay, now we update k equal to c. In this case k will become 1, some score will become s of 1 or the score of 1, right? The important thing is walk is set to true, right? And then we increment hops and exit the loop, right? Now remember k is holding the value 1, we have exit the loop, so we will no longer go back to the for each, right? And since there are no statements after this line here, we go back to the while, right? Next step of the while, and walk is true, remember. So we enter the loop. Now for each c in columns of a, if a of kc, right here remember k is equal to 1, so now we are going to check all the columns here but corresponding to this row. So is a of 101? No. So we go to the next one. Is a of 111? Is a of 121? No. So none of these are satisfied. A of 13 equal to 1, so we'll enter the if block. Right now k becomes 3. All right, some score is nothing but s of 3. All right, and then we are again setting walk to true, we go back. Okay, walk is true now. So for each c in columns of a, is a of 301, is a of 311, a of 32, a of 33, and a of 34. Since none of these are 1, we don't enter this if block at all. And since we don't enter the if block, walk remains false. Walk is never updated to true. So when we exit out of the for each, we also exit out of the while because walk is false. Okay, so that is what is happening in the pseudocode. So what exactly is this in as far as the graph is concerned? See, remember what we did. We started with node 0. Whenever node 0 had some outgoing edge, we jumped onto that. We hopped onto that. So in this case, 0 had an outgoing edge from 0 to 1, right? So we went to that particular node. And then we again checked for an outgoing edge from 1, right? Since there is an outgoing edge to 3, we jumped or hopped onto that. And then we checked if 3 had any outgoing edges. Since 3 does not have any outgoing edges, we stopped there. Okay, so what this pseudocode is trying to do is it is trying to hop from one node to another node. It keeps hopping until it can find no more neighbors to hop to, right? So it started from 0, it hopped on to 1, and then it hopped on to 3. Since 3 has no more outgoing edges, it's going to stop at 3. All right, this is what the pseudocode is doing. So now let's look at the questions, right? So which of the following statements about sum score is true? Okay, so if you notice, it is nothing but the minimum score in the table. So why is this true? It is because every time we hop, right? Every time we hop, we move to a node with lower score. All right, let's look at this graph. Every time we hop, right, we go from a node which is having higher score to a node which is having lower score. All right, so s of I is always going to be greater than s of j whenever we hop from I to j. So if we keep doing this, we will reach a stage when we cannot hop to any other node, right? We will reach a node k where we cannot hop anymore. So that means for that particular node, the score is less than or equal to the score of every other student in the table. So s of k is less than or equal to s of I for all I in 0 to n minus 1. Only then will k have no outgoing edges, right? So we have reached a node or we have reached a student with minimum marks in the table. Okay, so that is subpart A. In subpart B, remember this is an independent subpart. We are given that hops is equal to 0. Okay, so when will hops be 0? Let's go back to the pseudocode. Hops will remain 0 only when this if block is never executed. Okay, When will this if block never be executed if this condition never becomes true? This means for k equal to 0, there are no outgoing edges, right? Only then will k never be updated. Only then will any of these variables never be updated, right? So for k equal to 0, there are no outgoing edges. That is, a of kc is never 1 for every c in the columns of a. This means k equal to 0 has scored the minimum marks in the class, right? Only then can there be no outgoing edges from k, and that is exactly the answer for this question. The value of k is equal to 0 and k has scored the minimum marks in the class. Next, we have the variable hops satisfying some inequality, and what is that inequality? Right, so we have already seen that hops can be 0, and as hops is never decremented or as hops never decreases in the inside the if block, hops is always going to be greater than or equal to 0. So the only thing we are going to worry about is the upper bound for hops. So for that, consider this kind of a table in which student 0 has scored more marks than student 1, student 1 has scored more marks than student 2, and so on, right? So if you look at the matrix for this particular table, all the entries above the main diagonal for this matrix will be 0, will be 1, right? For this matrix, all the entries, all the cells above the main diagonal will be 1. Now why is that the case? So what are the entries above the main diagonal? If I corresponds to row and j corresponds to column, then j greater than I will correspond to all entries above the main diagonal. Okay, and whenever j is greater than I, we know that s of I is greater than s of j. Alright, so this might take a while for it to sink in. Notice that s of I is greater than s of j for all j greater than I. Okay, so for example, s of 1 is greater than s of 2, s of 1 is greater than s of 3, and so on. So s of I in general is greater than s of j for all j greater than I. So all j greater than I is nothing but all entries above the main diagonal, and for all such entries a of ij equal to 1. Okay, so if you execute the pseudo code for this particular graph, what will happen is we will start with node 0 and we'll hop to node 1 because there is an edge from 0 to 1, and 1 is the first column in columns of A for which A of kc will be equal to 1, if you remember. So A of 0, 1 will be equal to 1, and in row 0, 1 will be the first node for which there will be an edge, or the cell will be having a value 1. So we'll hop to node 1, and for node 1, if you look at the row of node 1, 2 will be the first column or first node for which A of kc will be equal to 1, right? So we'll hop to node 2. Likewise, we'll keep hopping to successive nodes. So we'll make a total of n minus 1 hops, right? And also note that since there are only n nodes, we cannot do more than n minus 1 hops, right? We are already on a particular node, node 0 to start with, and we can hop at most n minus 1 times, right? And that gives us the bound 0 less than or equal to hops less than or equal to n minus 1. And finally, we come to the last part in this question. So we begin with sum equal to 0, and for each c in columns of A, we are accumulating A of kc in the sum, in the variable sum. So if you remember, k corresponds to the student with minimum marks. As student k with minimum marks has no outgoing edges, A of kc will be 0 for all c, right? This means sum will remain 0, and sum is nothing but the out degree of node k in the graph, right? And that ends the solution to this problem. So in this question, we have a new graph GR that is obtained in the following manner. So for a pair of students I comma j, there is an edge from I to j if and only if i's score is strictly less than that of j, right? If you remember in the earlier problem, there was an edge from I to j if i's score was strictly greater than that of j. In this question, we have a graph GR where this relationship is reversed. So there is an edge from I to j if and only if i's score is strictly less than that of j, right? And the matrix for this graph GR, we represent it by B, and we are trying to compute B from A, right? Assume that A has already been computed. So here what we do, we initialize the matrix B and then we go through each row and column of A, right? So let's analyze this graph GR and G before arriving at some decision. Okay, so notice that if there is an edge from I to J in G, then there is an edge from J to I in GR. Okay, so to see why this is true, if there is an edge from I to J in G, then S of I, the score of I, is going to be greater than score of J, which means that the score of J will be less than the score of I, right? And according to the definition of GR here, there is an edge from J to I if the score of J is less than I. So there will be an edge from J to I, right? This is also true in the reverse direction. If there is an edge from I to J in GR, then there is an edge from J to I in G for very similar reasons, right? So in a sense, there is a bijective relationship between the edges of G and GR. Okay, so all that we have to do is, whenever you have an edge from I to J in G, we have to put an edge from J to I in GR. Okay, so in terms of matrix notation, what we have is, whenever A of Ji is 1, which means there is an edge from J to I, then we have to add an edge from I to J in GR. Since the matrix corresponding to GR is B, we set B of Ij equal to 1 whenever A of Ji is equal to 1. Okay, another way of doing this is setting B of Ij equal to A of Ji. If A of Ji is 1, then B of Ij should become 1. Likewise, if A of Ij is 1, B of Ji should become 1. If it is 0, then there is nothing that we have to do about it. B of Ij will also be 0 if A of J is 0. The only case we have to consider is when A of Ji or A of Ij is 1, then that reverse direction, that reverse relationship should hold for B. So whenever A of Ji is 1, B of Ij should be 1. And whenever A of Ij is 1, B of Ji should be 1. Alright. So that brings us to the last subpart. If for a pair of nodes I, j we have this relationship holding, what can we say about the scores of I and j? So there are two possibilities, A of Ij, B of Ij both being 1. But clearly this cannot happen because we cannot have I having greater score than j while simultaneously j having greater score than I. So this is not a possibility, which leaves us with the only possibility where A of Ij and B of Ij are both 0. From this it follows that S of I should be equal to S of j, right? And that is what we have selected here. So that ends the solution to this problem.